Hey there, it's Workbench or Workbench Quagmire back with day 68. And check real quick. 68 out of 100. 100-ish days of our free code camp Python certification. Today we're going to go through these first 3 theory sections, and then we'll do the next 3 tomorrow. And then the day after that, we will do our linked list workshop. It's a relatively short section here on linear. Let's collapse all this down. Yep. So basically 3 of these, our workshop, no lab, review quiz, and certification project. So let's get started with what is an algorithm and how does big O notation work. So every computer program that runs on your device has a specific set of instructions which are executed in a specific order to complete a task. The task could be sorting a set of numbers, modifying an image, tracking inventory, or even running your favorite video game. This is where algorithms come into play. An algorithm is a set of unambiguous instructions for solving a problem or carrying out a task. You can think of an algorithm as a recipe. When you cook, the recipe lists all the ingredients that you'll need and provides a step-by-step instructions on how to prepare a dish. Equivalently, you could think of an algorithm as recipes that tell computers exactly what should be done and how to do it. Algorithms have 2 key characteristics. They cannot continue indefinitely. That's called a infinite loop. They must finish in a finite number of steps. Each step must be precise and unambiguous. They may have 0, 1, or more inputs and generate 1 or more outputs. The steps of an algorithm are independent from any programming language. But to actually make them run on a computer, you need to implement them in a programming language like Python or JavaScript. If an algorithm is correct, the output for any valid input should match the expected output. In addition to being correct, algorithms should also be efficient. Algorithm efficiency can be measured in the terms of how long they take to run and how much space they require in memory to complete the task. Knowing an algorithm's efficiency is very important because it gives you an idea of how well it will perform if the input size grows, or as the input size grows. For example, sorting 15 integers is not the same thing as sorting 1,000,000 integers. As the process grows in size and complexity, if the algorithm is not efficient enough to handle it, you might end up with a very slow computer program that may even crash the entire system. That's why it's important to develop and choose the most efficient algorithms possible. This is where big O notation becomes very important. Big O notation describes the worst case performance and growth rate of an algorithm as input size increases. The growth rate of an algorithm refers to how the resources it requires increase as the input size grows. Big O notation focuses on the worst case scenario or worst case performance because this is a case that's very important to understand how efficient the algorithm can be, even in the worst case scenario, regardless of the input. Going back to our sorting algorithm, or our sorting example, sorting 1,000,000 integers should intuitively take more time and resources than sorting 15. But how much more? This really depends on the algorithm that you choose to sort them. Big O notation will not give you an exact number to describe the algorithm's efficiency, but it will give you an idea of how it scales as the input size grows, based on the number of operations performed by the algorithm. In Big O notation, we usually denote input size with the letter N. For example, if the input is a list, N would denote the number of elements in that list. Constant factors or lower order terms are not taken into account to find the time complexity of an algorithm based on the number of operations. That's because as the size of N grows, the impact of smaller terms in the total number of operations performed will become smaller and smaller. The term that will dominate overall behavior of the algorithm will likely be the highest order term within the input size. For example, if an algorithm performs 7n plus 20 operations to be completed, the impact of the constant 20 on the final result will be much smaller as n grows. The term 7n will tend to dominate, and this will define the overall behavior and efficiency of the algorithm. Another example would be an algorithm that takes 20n squared plus 15n plus 7 operations to be completed. The term 20n squared will tend to dominate as n grows, so this algorithm would have a quadratic time complexity because the dominant term has n squared. Quadratic time complexity is one of the many different types of time complexities that you can find in the world of algorithms. Let's learn about some of the most common ones. So 0, 1. This is known as constant time complexity. When an algorithm has constant time complexity, it takes the same amount of time to run regardless of input size. For example, checking if a number is even or odd will always take the same amount of time regardless of the number itself. So there's an example of our even odd kind of algorithm I think we looked at earlier on the project in the certification. 0 log n is known logarithmic time complexity. This means that the time required by the algorithm increases slowly as the input size grows. This is common in problems which the size of the problem is repeatedly reduced by a constant fraction. For example, a popular search algorithm called binary search has 0 log n worst case time complexity. This is because it eliminates half of the remaining elements each time elements in each comparison, which makes it more efficient overall. 0n is known as linear time complexity. The running time of the algorithm is with this time complexity increases proportionally to the input size. For example, a for loop that iterates over all the elements of a list will perform more iterations as the number of list elements increases. If the list is doubled in size, the number of operations will approximately double as well. For grade and grades, print grade. So the higher number here, the number of times we got to print it. 0 in log n is known as log linear time complexity. This is a common time complexity of efficient sorting algorithms like merge sort and quick sort. And then 0 n squared is known as quadratic time complexity. The running time of these algorithms increases quadratically relative to the input size, which is generally not efficient in real-world problems. Nested loops are a common example of a quadratic time complexity. The inner loop will perform n operations for each one of the n iterations of the outer loop, resulting in n squared iterations. So here's our nested for I in range, for j in range, print hello world. Other time complexities include exponential time complexity, denoted by O 2 to the n, and factorial time complexity, which is denoted by O in bang, or explanation. Factorial. Both are inefficient for real-world scenarios. In this graph, you can compare growth of the mathematical functions that represent the most common time complexities. Think of the x-axis, the horizontal axis, as the input size and the y-axis as the running time of the algorithm. You can see the quadratic time complexity, O into the squared, yellow, grows much faster than the other ones, which with constant time complexity, red, stays constant even if the input gets larger. So yeah, these are just algebraic equations. So it's sort of, if you understand what these shapes would look like, you know, like linears, just going to be this, you know, run one, rise one kind of repeating thing. You know, whereas the n squared is going to really go up there. Then you have your constant down here in the red, your log n, which is very close to constant. Great. So far you've learned about big O notation in terms of time requirements, but this notation also applies to the context of space requirements. In this context, it describes how the memory space required by the algorithm grows as the input size grows. Algorithms with constant space complexity always require a constant amount of memory space, even as the input gets larger. An example would be an algorithm that only creates and stores a few variables in memory. In contrast, the space requirement by algorithm with linear space complexity increases proportionally as the input size grows. An example of this would be algorithm that creates and stores a copy of a list of length n. And finally, the space requirement of an algorithm with quadratic space complexity, O to the n squared, increases quadratically as this input size grows. For example, an example of this would be creating a 2D matrix where the dimensions are determined by the input size, storing all possible pairs. Algorithms are the building blocks of computer programs, while Big O notation is a powerful framework for analyzing how efficient they are based on how their time and space requirements in the worst case scenario scale of the input size grows. Understanding their efficiency is very important for developing software that works efficiently in the real-world scenarios. All right, which of the following best describes an algorithm? Specific programming language? Nope. Step-by-step instructions designed to solve a problem or perform a task? I think that's choice 2. A type of computer hardware component? No. A software application used for developing, playing games? Nope. What is the primary purpose of Big O notation in the context of algorithms? To measure the exact time an algorithm would take to run on a specific computer in seconds? That's not true. To count the total number of lines of code in an algorithm? Nope. To describe how the resource usage of an algorithm grows as the input size increases? I think that's the answer. To determine the best case performance of an algorithm? I don't think that's true. That's the worst case. If an algorithm has a time complexity of O(n), what does it mean about its performance? The algorithm's running time increases proportionally with the input size. Yes. Algorithm's running time remains constant regardless of input size. No. The algorithm's running time grows exponentially. No, that would be n squared. Algorithm's running time decreases as the input size grows. No, I think it's number 1. Let's check. We got it done. All right. That took longer than I thought. These are a little more wordy. So I'm going to end this video here. We'll call it on this one, and we'll start next time with what are good problem-solving techniques and ways to approach algorithmic challenges, and carry on through our algorithm section here on our Free Code Camp Python certification. So, thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time.